There we go. Okay, we're recording. So yeah, I mean, I don't know if you guys have want to start off with any questions, anything on the homework. I know, Andrew, I don't know if you saw my email response this morning with your question about the Scott and Reinhardt approach.
Oh yeah, so is it like I just read like a bit ago. Is it like I think I redid the homework and looked at the passive fire stuff, and that had different numbers than what Rothermel had.
Yeah, exactly. So yeah, it sounds like you figured it out. But basically, right, the difference there is that in Rothermel, um, there is no passive crown fire rate of spread. He just assumes that either you're going to use the surface fire rate of spread or it's going to become an active crown fire. And then at that point, basically the rate of spread immediately increases by like 3 times or whatever. Instead of Scott and Reinhardt, they kind of have this gradient where as trees start to torch, the rate of spread is also going to kind of increase as a simple linear function with the number of trees or crown fraction burned, really. So yeah, it's that passive crown fire output that we were looking for on that one.
Okay, that's good. I was able to switch it around this morning.
Okay, good. Yeah, because I after I sent that email, I noticed you had already submitted it, so I was hoping you would. So it gives you the option to just like resubmit something. I've never done that.
Yep, it does give you the option to resubmit.
Okay, I guess yeah, up until the deadline tonight. All right. Well,
does this cover up to lecture 13?
yeah. So I'm gonna it's gonna include the crown fuel quantification stuff, but at a not a super deep level. Really the big thing, and I've kind of got like maybe 10 different slides here that I think hit on maybe what I think were the big themes or big pieces of content from those lectures. And so you'll have an idea of kind of what I'm thinking are the most important parts of that Canopy fuel lecture.
Cool.
Yeah. Okay. Well, I guess we'll go ahead and assume it's just going to be the 3 of us, and if anybody else pops in, great. So let me see. I'm going to try and share my screen. Sorry, I haven't been doing much of this. Speaker view. Okay. Oh, there it is. Okay, so you guys should probably see. I can't tell what you guys can see, but I assume it's a big slide that says Quiz 3 review.
Quiz 4, yeah.
Or Quiz 4 review, yeah. Okay, cool. So anyway, here are the topics. Sorry, I'm just still figuring this out. The topics it's generally going to cover. So we're going to have a little bit on the 2D spread and growth. So lectures 8 and 9, and then that previous Behave lab, and then all of our crown fire initiation and spread questions, and then a little bit on estimating the canopy fuels. So is there anything else? I guess it sounded like you guys didn't have any questions off the bat before we jump into the stuff that I put together.
Mm.
All right, so
Not really.
all right, so yeah, we'll just go through these.
Yes, yeah, going over this would be nice for sure.
Cool. So yeah, so let's talk about these diagrams. So this is a simulation that I set up last night, just kind of playing around with Behave. So I don't know if I guess my hope was maybe one of you guys wants to take a shot at kind of what's going on here, what kind of what type of fire are we simulating, what all these arrows mean. . 'Cause,
Um, sure. It's the spread from the ignition point.
Yep,
So,
so that's correct. That's the method we're using here for this calculation.
okay. And the surface fire spread direction should be the max spread, or the max spread is 96 degrees, so that's where the head fire is going.
Yep.
And the blue arrow seems to be a flanking fire, or a flanking.
Yeah, probably close to it, right? So a flanking fire, and I wish that these diagrams would tell you maybe like the angle between these two arrows, because just looking at it, like it's not quite a right angle, so that tells us it's not exactly flanking, right? Because flanking fire would be 90 degrees relative to the direction of maximum spread. So we're, yeah, it's not quite flanking, but it's definitely not heading. So maybe a little closer to flanking than heading, but yeah. So this fire this basically means, and I don't actually remember the degrees I put in here for my spread, direction. But yeah, so clearly it's not a head fire, and it's maybe not quite a flank fire. And then these other arrows, right? So the blue and the green arrow are showing us where the wind is coming from on the blue, right? And so we've got a wind coming. Where's the wind? What degrees did I put in to behave to get that wind?
So it's 90 degrees from north. So I think 90 degrees or 90.
So it's in this case it's actually blowing out of the west to the east. So I put in 270 for my wind direction, right? That's saying the wind's coming out of the west. And then we have a north facing slope, right? Because upslope is going south. So that means this north is, or the face is the slope is facing north. Yeah.
Okay.
Cool. Yeah. So these are pretty useful. I like to always output this image whenever we're dealing with wind and slope that aren't in alignment. It just helps visualize what you're actually simulating. Cool.
Yep.
All right. You got anything, Will?
No, I don't have anything.
Cool.
I'm just trying to stay muted because I have 5 roommates. So.
Okay. Yeah. No, that's fine. I guess I'll just leave it to you then. If you have a question or whatever, you'll jump in.
Okay.
Cool.
Sounds good.
All right. So yeah. And then anyway, I just put this picture up here because it helps to kind of visualize what's going on here. Where right, we've got our wind and our slope aren't aligned, so the direction of maximum spread is going to end up being kind of somewhere in between. Cool. All right. So in terms of 2D spread, and then how we might do this in behave, right? We have these two options for directions from the fire perimeter, or we can do directions from the ignition point. So I don't know if anyone of you guys wants to tell me about the difference in terms of, like, if we put in 90 degrees, how does that differ if we're measuring that from the perimeter versus from the ignition point? It's okay if not. I know that there's only 2 of you, so I'm putting you on the spot.
So 90 degrees from the ignition point is going to be like a little shorter than what's represented, or like from the ignition point to the edge. It's
Right.
a short distance, but 90 degrees from the fire line, it'd be right from the exact middle.
Mm-hmm. So that's right. So what does that mean in terms of the fire behavior? If we did the same simulation and we just changed from perimeter to ignition point with that 90 degrees, which one of those would have a faster rate of spread?
The fire line.
Right. Yep. And that's basically because the 90 degrees from a perimeter, fire perimeter, right? That means we're describing flanking fire behavior. 90 degrees from the ignition point is going to be more closer to backing fire. Can you guys see my mouse on here? Or is there a way I can?
I think I see your mouse.
Yeah. Okay. So I can kind of like point to stuff with it.
Yeah.
Okay. So yeah. So yeah, you basically got it. And then here's just another image of kind of what that looks like in terms of from the ignition point. And so you're spot on here, where 90 degrees from the ignition point means we're simulating something closer to a backing fire versus the flanking. And so that just, it's just important to remember the differences here and when you might want to use one versus the other. All right, cool. Crank it through. Okay, so that's all I got for the 2D stuff. I was gonna put in another slide that I think I forgot to, talking about that campfire growth calculation that we did. So I would just suggest kind of going back to those slides and kind of refreshing yourself on how that rate of area growth thing works, and maybe why that's different, and tells you something different about the fire behavior or the fire spread than just a rate of spread. Okay. So Van Wagner set up this framework for us in terms of how we define. This is annoying. I guess I'll just hide it. How we define different types of fire. So I kind of put it all up here, right? So the way it works, and actually maybe I won't go through and tell you the way it works, and I'll let you guys maybe tell me a little bit. Right. So how do we know if it's going to be a passive crown fire?
Maybe a passive crown fire if the surface, the eye surface is high, or but the crown rate of spread is low. It's able to spread from the surface into the crown pretty quickly, but really not be able to continue on faster.
Right. So you got that. So where do these values come from? Where do we get eye surface?
Eye surface is the intensity.
Yes. Yeah. So that's just whatever the surface fire intensity is. In our case, right, we usually will get that from Rothermel 72. But theoretically, you could also use like a field measurement or something. And then what is the I prime or I initiation?
The I initiation is the intensity, or like the intensity required to have the actual crown fire initiation.
Right. So that's coming from Van Wagner. So do you remember what goes into that equation to calculate the critical intensity required?
Can you repeat that?
What variables determine the I initiation?
The initiation, I do not remember.
So I don't think I have the equation on here, but it is right. So it's Van Wagner's critical ignition, or or what was it, critical surface fire energy or intensity. And so it's based on the crown base height, right? How far above the surface is our crown fuels, and then the canopy fuel moisture as well, right? Because that influences how much energy is required for ignition. All right, so mostly got that. So now, in terms of active crown fire, we need both sufficient surface intensity, and then we also need our predicted rate of active spread to be high enough. So do you remember where, I guess we'll start with our prime, so our critical rate of spread required for crown fire, for active crown fire. How do we determine that?
The critical rate of spread.
The critical rate of spread, yep. And this is also coming from Van Wagner.
So the critical rate of spread is the fire line intensity that is needed for it to be a crown fire, or is drawn from crown base height and how much heat needs to be transferred to start an ignition or the heat flux.
Yep. So that's the I side, the initiation side of the equation, and then there's an additional question that we have to then ask is, right, now that we've ignited our crowns, do we expect that to continue to propagate as an active crown fire? And what Van Wagner said is that basically there's this critical mass flow rate needed to sustain the active crown fire, and so that is going to be based on the bulk density of the canopy, as well as how fast the fire is spreading. And so I've got another slide. We can delve into that parameter a little bit more. But basically, it's based on the bulk density of the canopy, and then our estimated, or sorry, not our estimated, our this critical value or physical limit that Van Wagner identified. And so we'll maybe we'll look at that on the next slide. The other part of that is the R active. So basically, how fast, if it were a crown fire, how fast would we expect it to go? And so that side of it just comes from Rothermel 91, and we'll talk about that more too. So anyway, this is the fire types from Van Wagner, where we're kind of linking Rothermel 72 and 91 with Van Wagner to make these predictions. All right, so here is this concept that there's basically some critical amount of fuel in the canopy that needs to burn every second in order for active crown fire to be possible. And this amount of fuel that's consumed, we can calculate it by basically just multiplying the rate of spread by the canopy bulk density. Right? So rate of spread in meters per second times the bulk density in kilograms per cubic meter basically tells us how many kilograms of fuel we need to burn every second within this vertical plane, this area, right? So in this concept from this old AG paper, you can see there's this vertical plane, and we can imagine the forest is moving through it, and we need to move the forest through it fast enough in order to produce, in order to burn enough fuel and produce enough energy to sustain that fire in the canopy. And so basically, to figure out what this critical mass flow rate is, Van Wagner did this series of experiments and basically calculated this value as 0.05 kilograms per square meter per second. So that's kind of the concept there in terms of, what's required to sustain the active crown fire versus just having a passive torching kind of fire. Sorry, it's kind of loud. It's getting a little hot in the office. So any questions on this concept here of, and there's more details on sort of the math behind this and you know, why there is this critical amount of fuel that needs to get burned in the lecture. Now I'm forgetting my lecture numbers. I think that's lecture maybe 12, no, 11, probably lecture 11. Anyway, so any questions while we're on this right now?
Not for me.
Not from you? Okay. Cool. All right. So there's our critical mass flow rate to sustain this active crown fire. And this ties directly to what we try and do a lot of times when we're manipulating stands. So I like this image here because it really shows how basically what we've done here in this treatment is reduce the canopy bulk density significantly. So significantly that even just looking at this picture, you know, it should be pretty obvious that we're not going to be able to have an active crown fire, at least in that one stand there. You know, the foreground here looks pretty dense, but you just won't be able to sustain an active crown fire because there's not enough fuel available to burn, and it's basically too separated from each other. Cool. All right. And so here's what that looks like. So basically we've got this S0, which is the 0.05 in the equation. And if we divide that S0 by the actual bulk density, it will predict a critical rate of spread that would be required to sustain active crown fire. And so, you know, this chart here on the right shows this nicely, that basically if we have a really dense forest, so over here on the right side, 0.3, 0.4 for our bulk density, we need a slower rate of spread to sustain that active crown fire. So we basically don't have to, well, we're burning basically the same amount of fuel. It's just we don't need a super fast spread rate to burn enough fuel to keep that fire up in the crowns. And then at a certain point, right, our bulk density gets so low that in order to have an active crown fire, we would need, you know, an unrealistically and impossibly fast rate of spread. So at a certain point, we've thinned our forest to a point where it just, you know, it just wouldn't be physically possible to get that horizontal tree to tree spread required to be an active crown fire. And then the other point here, right, is that this Van Wagner 77 doesn't tell us anything about what the active rate of spread actually is, right? This is just a criteria to determine if it is even possible to sustain that active crown fire. And so we'll need another model to predict, you know, once the active spread starts, what the rate of spread would actually be. And so that's going to be from Rothermel 91. Yeah. So anything on this? Cool. All right. So here's our Rothermel rate of spread equation. So it's pretty straightforward, and yeah, I'm hoping one of you guys can remember how this worked and maybe tell me a little bit about it, and then potentially answer that question I have here on this slide.
I think it's a wind-driven rate of spread.
Yep,
or,
that's correct.
From what I remember,
Yep. So he says, oh, weird. Okay. I guess that's good. It's not going to kick us off. I thought anyway. Yeah. So he says right at the beginning that this is only for wind-driven crown fires. So those are fires that, you know, the wind speeds tend to be on the higher side, and it's really that you know, that ambient high level winds that are pushing our fire and dictating the rate of spread and the spread direction.
Hey Scott, can you there's like a thing that says this meeting has been upgraded by the host, and it's in the middle of the slide.
Oh, weird. I just clicked. It's gone on my screen. Can you? You can't.
Oh, that was on my screen. I see.
Yeah. Yeah, that's weird because I'm using the university's Zoom account right now, so it shouldn't have even been an issue in terms of the time limit. But anyway,
Okay. I thought that was on yours because it popped up on the slide.
yeah, yeah, cool.
Yeah.
Um,
Never mind.
it's all good. So yeah, so these are for wind-driven fires. I don't know. Do either of you guys remember? I think I definitely talked about it a little bit in the lecture, but what is a plume-dominated fire, and then maybe why this equation wouldn't work so well for a plume-dominated fire?
I don't remember.
Okay.
If it drives itself,
Sorry.
a fire that makes its own wind.
You mean basically that's a decent way to think about it, because essentially what's happening in plume-dominated fires is that either because the you know, the ambient wind isn't as strong, or because the fire itself just has so much energy that the energy from the fire is really dominating the atmospheric conditions, and so that really strong convection plume coming off of the crown fire, yeah, it starts to basically develop its own weather system, so it's driving the inflow into the fire, and so basically you just get these really sort of complex effects where it's hard to predict, and it's not necessarily going to spread in a, you know, super kind of linear or predictable fashion. And those fires also tend to be well, maybe that's not true. I was going to say that they tend to be kind of more extreme, but it's more it's just more about what's driving the behavior. And in the case of a plume-dominated fire, there's a lot of interactions between the fire and the atmosphere that make prediction about them a lot more complex. Excuse me. So yeah, so these are all for wind-driven fires, and basically, right, what Rothermel did is he got this collection of a data set of all these different wind-driven crown fires, and you can see when you plot them here, there's a pretty nice relationship. And so I guess back to his equation for what is the active rate of spread. So the correlation he developed is basically 3.34 times the rate of spread that would be predicted for fuel model 10, assuming this this large wind reduction factor, which actually means that we're not reducing the wind as much as if this were smaller. Remember, if that was like 0.2, we'd have even a lower winds. But yeah, so it's this idea that we first predict the surface fire rate of spread for fuel model 10, given all of our other weather conditions, and then we multiply that by 3.34, and we'll get a pretty good prediction on how fast that fire would move if it were a crown fire. Right, and then so back to this this slide here. So we could go ahead and compare that R active from Rothermel 91 with the critical rate of spread, the R prime, from Van Wagner 77 right here, right? And so if the Rothermel prediction is greater than Van Wagner's critical rate of spread, we now would assume that we're going to have active crown fire behavior, and that crown fire is going to have this, whatever we calculated here, whatever our active is. Cool. And then we also have this option that we talked about at the beginning, where Scott and Reinhardt introduced this idea of passive crown fire rate of spread. That just kind of fills this gap here between surface fire and active crown fire. And basically, right, the way that it works is this is a nice plot here where as we increase our open wind speed, we would get a faster spreading and more intense surface fire. Once that surface fire is spreading fast enough and producing enough intensity to start initiating tree torching, in the Rothermel 91 method, we would continue to predict surface fire rate of spread up until the active portion starts. But anyway, Scott and Reinhardt introduced this idea that, hey, once we start having torching, we probably have some increase in the rate of spread. And they basically just assume there's this linear relationship here between the crown fraction burned and the rate of spread. So we just kind of draw a straight line between our surface fire rate of spread and active rate of spread to predict the passive portion of the fire. And in Behave, this isn't the default option, but I think that most of the other operational fire models in the US, I think, just use this approach by default, where we're assuming that there's something different about passive crown fire and that it's going to spread a little bit faster than a surface fire. And I think there are probably arguments on either side of how justified this linear relationship is, and it probably varies a lot from fire to fire. So I'm just maybe a little caution in this passive zone. But anyway, so that's the Scott and Reinhardt method that we can use in Behave. All right. Let me just remind myself. Okay, so we got a couple slides here about our Canopy fuels. Get you guys out of the way. So I think a key thing that I talk about in that lecture is canopy base height. It's a very, very important parameter in terms of crown fire prediction. And I mentioned that there's a number of different ways that we can measure this, or methods we can use to calculate it. So I've got this example here from the presentation where we've got this data from a 10th acre plot, right? And if we take the average crown base height of all those trees, we end up with 4.2 meters. If we were to take the lowest crown base height, it's a lot lower, 1.9 meters. Or there's also this percentile method. So the 20th percentile is 2.1 meters, right? So these are pretty different values that have pretty big implications. So in addition to changing canopy base height, what other parameters get changed? So thinking about our ways that we quantify the canopy fuel complex, what else changes when we say go from a canopy base height of 4 to a canopy base height of 2?
The volume, or
exactly.
The fuel.
Right. So when we drop the canopy base height down, we're now taking the same canopy fuel load, and we're going to have a larger volume that is distributed throughout, which means the canopy bulk density is going to go down. So in terms of our crown fire, modeling or crown fire prediction, what implications does that have?
More fuel?
Yeah. Did you determining like what did you say?
So this other question I have on here, in
Oh,
terms of potential crown fire behavior, what implications does going from canopy base of 4 to a canopy base of 2 have?
quicker crown fire spread, right?
Right. How does it affect it?
Affect the spread. It
Yeah,
increases.
or even just the potential for spread.
It increases it.
So when we drop our canopy base height, it'll make initiation easier, right? Because we're saying, hey, these fuels are closer to the surface. So initiation will happen easier, but our bulk density has actually gone down, right? Because we've got a larger volume.
Okay.
So a lower, right? Remember, a lower canopy bulk density means basically what that's saying is that it would potentially be harder to have an active crown fire now. So we would need to have a faster rate of spread to sustain that active crown fire. So really the point is that this variable is really actually in this case kind of would have a contradictory effect. It would say that it would be easier to have passive crown fire or easier to have torching, but more difficult to have an active crown fire. And it's the exact same stand, right? It's just all about how we pick or what method we use to identify canopy base height. Cool. All right. And then the last slide here, I think these canopy fuel profiles are really cool and useful, and they tell us a lot about the stand. Both if you're, honestly, even if you're just a forester or silviculturist, and you're not worried about crown fire behavior, I still think these plots are important because they really tell you how your trees or how your foliage is using the growing space. And they can tell you also a lot about what the actual forest structure looks like. So this is a plot from the Reinhardt 2006 paper that is up on Canvas if you're interested in checking it out, where they destructively sampled all these stands. So these should be pretty good measurements of the actual fuels that were there, and then we can draw all these different plots for the different stands. So what do you guys think about those questions I got there based on this figure?
So the torching would be the tenderfoot lodgepole, the blodgett Sierra Nevada mixed conifer, and then the easier to sustain active crown fire looks like salmon Douglas fir lodgepole.
Yeah, so that one for sure.
And maybe Flagstaff.
Okay, yeah. So Flagstaff's probably the second one, right?
Yeah.
So I think that's pretty good. For the torching, I would probably. So what you said, you thought maybe tenderfoot.
Yeah, the solid line, maybe, but definitely the dashed line.
So why do you pick those?
Because it's a lower canopy bulk density.
So for torching, really the only variable in our torching equation, right, is the moisture content, which we'll go ahead and assume is the same in all these, and then the crown base height. So I would probably argue that it would be the what is this, the 9 Mile Pondo one, just because there's more fuel lower in the canopy here.
Yeah.
Right? That's
okay.
what this is showing us, right? Is there's more fuel down low, and so it might be minor, and it'd probably also depend on how you measure your crown base or your canopy base height, right? But that's what I see here is more fuel low in the canopy. And I also mentioned in the canopy fuels lecture that Another way of measuring canopy base height is to say to use a bulk density cutoff. I think typically one that gets used is oh crap, what is it? I think it's, I could go back to that slide, but basically, say our bulk density cutoff is 0.5, we just could draw a straight line here above 0.5. Oopsies. And whenever we hit a line, that would be its canopy base height. So that's just another method, basically saying that we need some minimum amount of fuel for it to be relevant, really, in the canopy. But so yeah, I like these. And then, so the active crown fire, Will, you totally got, right, the higher bulk density, and then also the fact that that high bulk density is really concentrated here. This it's not a super tall spread out stand. It's like all that fuel is really compressed. And so that would mean that it would be easier to sustain active crown fire. We would need a lower active crown fire rate of spread. So yeah.
What would a fuel treatment look like?
Yeah, so it would depend on the prescription, right? I mean, one thing, say we did like a thin from below, and that was the only thing we did. You basically say we did a thin from below on this 9-mile ponderosa. See, it's got this big chunk of fuel here down low in the canopy, and if we did a thin from below, we could just cut that off, and so now our line would go here, and then it would just drop right down to 0, and we just basically be removing all of that fuel volume through our treatment. Or if we did so we'll go back to our salmon, Doug fir, lodgepole, pine. This is probably a relatively homogeneous stand, so maybe we're going to do a crown thinning, maybe thin the spacing or something like that. We might not change the shape of this curve at all. We might just shrink it back towards maybe the Flagstaff curve there, right? So it would be the exact same shape, but maybe our peak is now, down here somewhere lower. So maybe we haven't necessarily changed the torching potential because we did, a crown thinning, but we've changed the potential for active crown fire by doing that. That
okay, cool.
Yeah, cool. And yeah, if you check out that Reinhardt 2006 paper that this came from, they have a bunch of plots showing how different types of treatment would change every one of these curves. So if you're curious to look more, it's there in that paper that's up on Canvas. So
for this big quiz, how many questions is it? Since it's a big quiz, is it like mini tests?
It's not crazy. I would there are 6 questions, and they're a little more. I actually didn't end up doing any math or even any behave in it. Like I said, I might. I just am kind of going for more concepts, so they're kind of short answer type questions for the most part. Just like a few sentences for each one, just to kind of make people think about the material more than just pulling facts from the slides. And yeah, my intention there is that it's going to be, I'm not presenting any other material or anything on Monday, so it'll just be basically your whole class period or whatever, however you want to think about it to work on it.
Is there a time limit on it, or?
No, I think I said it in the email, but I'm gonna make it available. Like I can set it automatically, so it's just gonna become available at 12:01 a.m. on Monday morning, and it's gonna close at 11:59 p.m. on Monday night. So you'll have all day to work on it.
Okay, cool.
Yeah. Any other questions?
I think that's it for now.
All right.
Yeah, I guess. I mean, are we gonna do another Zoom meeting since no one showed up?
I don't know. I mean, I appreciate you guys coming, and hopefully people check it out.
I mean, I think it's helpful, but
I think so. Yeah, I mean, I think so too. I'm sure. I would imagine you guys have a better grasp on some of this stuff now.
yeah, I don't know how I don't know if how to get more people on, but maybe like an incentive or something. I don't know.
Yeah, that's a good idea. Maybe just give some free points because
Yeah,
I don't
because
know. I
that
mean,
would also, I mean, the more people that's on talking about it, the better it helps me too.
Oh, 100%. No, I mean, I didn't expect everybody to be here. I was hoping it would be a few more people, but yeah, I mean, the only reason I didn't want to make it like mandatory or whatever
Yeah.
is that I know people have got all sorts of different stuff going on right now and might truly not be able to do it.
Yeah.
So I was I didn't want to punish people for not being here, but maybe we
I
could.
definitely know that. I know some people that could have definitely got on. They're just being lazy.
Yeah. So yeah, I guess I'll think about how to do that while being fair.
Yeah, I don't know.
Okay, cool. Well, anyway, I hope you guys are doing well. I appreciate you logging in.
You too, man. Be safe out there.
Yeah, thank you. Cool. All right. Well, shoot me an email if you need anything, and yeah.
All right, sounds good.
Cool. We'll talk later.
See ya.
What do I do? Stop recording.